Okay, picking up where we left off from last video, we're now looking at question number 6 on homework 8. This time around we have two train cars that are coupled together by being bumped into one another. Suppose the two loaded train cars are moving toward one another, and the first one has this amount of mass and a velocity of this much, so moving in the positive direction. The second one has a little bit less mass, but moving in the opposite direction. So what's important to note this time around is that they end up being coupled together, and when two items collide and then they get stuck together, we call that a perfectly inelastic collision. And what we note is while the first object has a momentum m1 times v1, the second object has a momentum m2 v2. By the time they collide, the mass 1 then gets combined with mass 2, because they're now one object, and they have a final velocity, v3, by the time they're finished. So I think if you set up an equation that looks something like this, you can compute v3, the final velocity, and answer this question. Question 7 is virtually the same problem, although it's a bit more morbid. You're driving a car, you hit a deer, and the deer gets stuck on the car. Don't know how that happens, but that's the scenario that we're looking at in problem number 7. In question number 8, part A, that looks just like the same question as before, but in part B, we start getting into this discussion of kinetic energy and how much of kinetic energy is lost or not conserved during an inelastic collision. And so with part B, we just have to remind ourselves that if object 1 is the first skater, then object 2 is the second skater. So we have two of them, one that was stationary and one that was actually moving. And then system 3, or item number 3, is the combined skater 1 and skater 2 after she or he jumps into the arms of the other skater. We should note that in scenario number 1, the kinetic energy belongs only to the skater that was in motion. So we have half of mass 1, velocity 1 squared, right? So at the beginning, only that first skater's mass mattered because the second skater, we can show it, has a mass, but the second velocity ended up being 0. So no kinetic energy from that second skater. So we can compute how much kinetic energy there was at the very beginning of the event, but at the end of the event, when the two skaters were combined, the kinetic energy ends up being half of the mass, which ended up being mass 1 plus mass 2, times the new velocity, velocity 3, that we get from part A, squared. And we're going to compare, how does this kinetic energy after the catch compare to the kinetic energy at the beginning? So with inelastic collisions, while momentum is conserved, kinetic energy is not. So let's find out how much kinetic energy is lost. Now for question 9, this one gets pretty interesting. We've got a hockey goalie with a particular mass catching a puck of a particular mass that was slapped at him, and that hockey puck has a particular velocity. The goalie and the ice puck have an elastic collision, so this is where the two bounce off of one another. And by description here, I think they want to say that it's perfectly elastic. You know, that doesn't really happen in the real world, but for computation's sake, let's say that it's a perfectly elastic collision, and the puck is then reflected back in the direction from which it came. We'd like to know what the final velocity of the goalie is and the puck. And so to address this, well, I'll just jump over to my solution set here. I want to point out that we should be referencing the elastic collisions between two objects formula. We've got this pretty wild-looking pair of formulas on our handout. And just to be clear, we have one formula that calculates the velocity of the first object at the end of the event, so v1 final, and we have a formula that calculates the velocity of the second object at the end of the event, v2 final. So the results for each of these are described as follows. You can see that at the beginning of each of these computations, we have some combination of masses that multiply by the initial velocity of object 1. Well, if we let, let's see here, if we let the goalie be represented by the number 1 objects and the puck be represented by the number 2 objects or 2 subscripts, the goalie himself wasn't moving, so we had a velocity of 0 at the beginning of the event. The goalie was stationary at the very beginning of all of this. So regardless of the combination of the masses, this whole section of the calculation turns to 0. And same thing down here, this whole section turns to 0 as well. So now, to calculate the final velocity of the goalie, we just plug in the mass of the puck, the mass of the goalie, the mass of the puck, and the speed of the puck at the very beginning, which was a positive 35. And to find the speed of the puck at the end of the event, we plug in all of the known quantities and the speed of the puck at the very beginning, and we should be able to compute the result at the end. So after we make those substitutions, assuming my math is correct here, these are the results we end up with. It appears that the goalie got pushed back a little bit. Got pushed in the same direction that the puck was traveling originally at 0.15 meters per second. And the hockey puck itself rebounded back at 35. Now it's important to note that it did not rebound at the full speed at which it came into the collision. In fact, it lost a little bit of speed. All of its energy was, or all of the energy of the system was conserved because it is a elastic collision. In elastic collisions, conservation of energy is still in place. So is conservation of momentum. But the speed ended up being a little bit less because some of that energy was transferred into moving or creating motion out of that prior stationary object. So I don't want you to think that the answer is always going to be the same speed at which it entered. It really was a little bit less. We only kept the 35 due to our significant figures. So, while I think those first 10 questions are pretty manageable, I'm sorry, that was only number 9. 10, I believe, is pretty manageable. It's number 11 that gets to be a little bit tricky. Let's talk about 10 real quick. At the top of a ramp, we have a mass that's 5 kilograms, and it's sliding down a frictionless track or ramp, and then it collides with another mass that's 10 kilograms, and it looks like the mass fell 5 meters. I don't think that was described in the problem, but our diagram shows that. So we could calculate the potential energy of the block when it's at the top of the ramp. We know that while we are transferring energy within the same object, the conservation of energy is in play here, and we can compute the new kinetic energy at the bottom of the ramp. That'll be equal to 1/2 mass velocity squared. And to be clear, we're not computing the energy. We know that these two are the same, but knowing that mgh, the potential energy at the beginning of the event, is equal to the kinetic energy at the end of the event, aka the fall and slide of this block, we should be able to calculate the velocity of that block at the end of the event. Now we know the velocity at impact, and when we combine the mass of block 1 with its velocity, we have its momentum, and we can also determine the new velocity of block 2 after the collision. Taking note that we're dealing with an elastic collision again, so we'll use the same set of formulas that we did in problem number 9. Now, moving on to number 11. This is where things can get a little bit tricky because we're not dealing with a head-on collision anymore. We actually have a glancing blow. We have an orange shuffleboard disc and a green shuffleboard disc that are going to collide. You'll notice that if this orange shuffleboard disc comes in this direction, it's going to glance into this disc and send it flying this way, and the orange one will kind of bounce off in this direction as well. And that's what this second set of diagrams is meant to show. This is obviously before the collision, and this is what's going to happen after the collision. Now our job is to determine the speed of the orange disk and green disk after the collision. And when we say speed, we do mean the velocity in the diagonal direction of the orange disk and the velocity in the diagonal direction of the green disk. So that's what we're after here. But the problem is that we have essentially two velocities that are combining together to make the diagonal velocity for each. We have a velocity in an x direction and a velocity in the y direction that allows us to determine the velocity in the diagonal. And I don't know of a way to answer this question to account for the direction of the diagonal velocities here without breaking this down into two parts. So we basically are going to need two computations, a series for horizontal motion and a series for vertical motion. Now, because this is an elastic collision, both kinetic energy and momentum is preserved or conserved, although I think we can answer this from the perspective of momentum only. Yeah, I think we can do that. So let's make a note here. We've got the mass of the orange block times the velocity of the orange block in the x direction at the beginning of the event. So all these subscripts are getting kind of wild. Mass of the orange times the velocity of the orange in the x direction at the beginning, plus the mass of the green times the velocity of the green in the x direction at the beginning of the event, must be equal to the mass of the orange times the velocity of the orange in the x direction at the end of the event, plus the mass of the green times the velocity of the green in the x direction at the end of the event. So there's our conservation of momentum. The sum of the momentums at the beginning must be equal to the sum of the momentums at the end. These subscripts get to be a little bit wild because of all the description that goes into them. Now there was an extra piece of information here. The mass of both disks are the same. So M0 is the same as mg. So I technically could have called all of these M0. And if you notice, M0 is common to every term on both sides of the equation. So mass itself is irrelevant. So because all of the masses are equal, this makes mass irrelevant in this computation. When we go to combine like terms and move things from one side to the other, they all disappear. So we won't have to worry about mass. But if we did have to worry about mass, if one was heavier or more massive than the other, then we'd have to be careful. Okay, well this is nice. The velocity in the x direction at the beginning must be equal to the velocity in the x direction at the end. Well, in this case, the orange block had a 5 horizontal velocity. The green block had a 0 horizontal velocity because it was stationary. And at the end, we don't know how fast it was going. But we do know that it's been bounced or shot off at a 37-degree angle. So what's kind of interesting here is that we don't actually have to have the precise horizontal velocity. The precise horizontal velocity would be equal to the precise final velocity in the diagonal direction times cosine of 37 degrees. Whatever the diagonal speed is, times cosine of 37 would end up giving me back the velocity in the x direction. So while it would be nice to have this number, we don't actually need it. And to be fully transparent, that's good, because this is what we're looking for. We want to know what the velocity along the diagonal would be for this particular object. Now, similarly, the velocity of the green object at the very end times cosine of negative 53 degrees would be necessary. I am using negative 53 here because it was shot downward at 53 degrees. If you want to use 307, I think that would be great too. Now we're talking about an angle in the unit circle. But now we're at an impasse, because while we have a nice simple expression on the left, on the right we have two different variables. The final velocity of the orange puck in the sorry, let me say that again. Final velocity of the orange puck at cosine of 37 degrees and the final velocity of the green puck at 307 degrees. We don't actually have one of those variables isolated. So our job is to get one of these by itself, or we need to solve for both of them eventually. But since we have two variables in the same question right now, we can't really go much farther than this. That's where having the set of vertical equations is going to come into play. Because we could take this one step further and say that the velocity of the orange puck at the very end is equal to some combination of these leftover terms. We could isolate this variable, for example. And once that's isolated, we still have a variable, the velocity of the green puck in the final velocity of the green puck. We could isolate this velocity of the orange puck and then use that quantity and substitute it in over here once we get a little bit farther with our vertical computations. And so it's like a system of equations from algebra class. We'll just solve this remaining system of equations and solve for one of the variables. I think at this point we'd be able to get the velocity at the end of the event of the green puck. We'll finally get a number for that. And once we have the number for the velocity of the green puck at the end of the event, we can bring it back over here and allow us to find the velocity of the orange puck at the very end of the event as well. So 11 makes you work a little bit. There are ways to set this up in matrix form, so if you want to try to explore that, you're welcome to. But solving it by hand this way I think works just fine too. So that's the direction that I kind of pushed you in for this one. I'm curious to see what you can come up with by the time you're finished. So I hope that pair of videos helps a little bit and you're able to work through the remaining questions. Again, problems 1 through 5 on this set had to deal with momentum and impulse, whereas questions 6 through 11 had more to deal with the conservation of momentum and a little bit about inelastic and elastic collisions. Make sure you send me a message if you're stuck on anything, and I'll try my best to respond to that. And I wish you all best of luck. We'll see you when you come back.